Welcome. Now today we will be discussing on the second week lectures and the assignments which is given to you. We will try to solve those assignments here. Now before we start on solving the problem, a couple of small corrections I would like to mention. One of them is you see at the lecture number 7 which is in the space segment, and there in the tracking we mention the word range accuracy. It's better we take it as a range resolution, which is the minimum count. There like phase measurement accuracy I mentioned, it should be taken as a resolution. Better take it in terms of resolution. So that is one correction, and there is one more correction which is a number by mistake which appears in the lecture number 8. That is we said where we were mentioning that the solar flux which is falling on the solar cell, the efficiency of the solar cell will degrade over the time the satellite is in the orbit, and a expression like this is given as E is equal to E of beginning of life. E is the efficiency of the solar cell, and then it says exponential and minus 0.043 t. It should be in the slide it was shown minus, this 0 was missed, it was shown 0.43. the correct thing is 0.043 t. This t is the number of years it is in the orbit. So please correct that expression. It is in lecture number 8, around 18 seconds after from the beginning, and lecture number 7, that is the accuracy should be treated as a resolution in the tracking. Okay. With these two small corrections, let us go to the assignments. The assignment number 1, it is based on the solar panel and the size of the solar panel calculation. A solar panel of a satellite is filled with 50,000 solar cells, and each cell is very small, 8 square centimeter each. That is the surface area of the cell, and 12% of the total area is reserved for the wearing. You cell to cell there has to be some gap, the wires have to go from the cell. So if you look at the total solar panel, there will be some percentage of the solar panel will be only wires, there is no solar cell. So that is about 12% of the total solar panel. So actual number of solar cells, when it is put, the solar cells each of 8 square centimeter each and 50,000 together will take 100 minus 12%, that is 88% of the total area will be taken by the solar cell. That is what. So these two numbers are given, and the total area reserved for wearing. Then calculate the area of the solar panel. It is a simple calculation. So number of cells is 50,000, already told, and so you can find out the total area occupied by only solar cells, which is this number of solar cells, that is 50,000 multiplied by 8, it says square centimeter. So, we will convert into meter, 10 to the power minus 4, which 8 into 5 40. So, it comes out to be 40 square meter. That is the total area occupied by the only solar cells, and we said the 12% of the total solar panel area is for wearing. So, the area of solar panel is this area of the solar cell, and 1 minus 12% of that, which is 40 by 0.88, which comes out to be 45.46 square meter, and our options which were given 55.5, 50, 45.5, 40. So, 45.5 is here. So, C is the answer. So, option C is the yes correct answer. That is simple. Now, let us take the second problem, which is reliability problem. It says that two systems of reliability 0.8 and 0.9 are connected in series. The overall reliability of the integrated systems will be, some numbers are given, different options 0.72, 0.85, 0.9, 0.98, etc. This is also very simple if you recollect that overall reliability when the units are connected in series. If this one is R1, this one is R2, then the overall reliability R0 is R1 multiplied by R2, and the numbers given are 0.8 into 0.9, that is 0.72, and the option is, first option itself is 0.72, then others. So, the option A is the correct option. Then the third problem is determine the power received by a VSAT terminal. VSAT is very small aperture terminal. We will discuss that one in later subsequent classes. By a VSAT terminal with effective antenna aperture. This term we are using now, later you will understand, but assume that is the effective area where the signal is captured, that is 0.098 square meter. The receiver terminal is 40,000 kilometer away from the transmitter. Let us assume satellite somewhere is there, satellite to this very small aperture terminal on the ground, the distance is 40,000 kilometer, and the transmitter transmits 20 kilowatt of power. That satellite is transmitting in this direction to the VSAT, total power of 20 kilowatt. So, the question is how much power is received in dB, careful, it is dBW, dBm, these some numbers are given. So, it is a very simple calculation, that is that power transmitted is 20 kilowatt, and at a distance of 40,000 kilometer the power received with the area of 0.098 square meter area, how much power is received there. So, this is solved, that is the power received will be the transmit power, that is 20,000 kilometer, 20,000, okay, that is 20,000 again kilometer, let me put, and then 0.098, which is the surface area, and then that power is at a distance it is going, that is 40,000 kilometer. So, the power flux which will be coming out will be 4 pi square r square, that is distance square, 40,000 kilometer, that square of that. And since the answers are given in dB, it is better to make it 10 log of that. So, if you calculate that way, it will come out to be 20,000 kilometer, and this is 40,000 kilometer. Sorry, this is not kilometer. I made a mistake. I am so sorry. I made a mistake. Somebody corrected me. It is not kilometer. This is power we are talking. So, this is 20 kilowatt. So, these 3 should not come. I was taking this one as a kilometer. I am sorry. So, let us rewrite the whole thing. So, the power received power is 10 log of 20 kilowatt, 20 into 10 to the power 3 watt, and it is received by aperture 0.098. Sorry, this is a mistake. So, this is the power transmitted in watt, and this is the aperture in square meter by 4 pi r square. R is 40,000 kilo, because we have convert this one is meter. So, convert this one in meter, pi r square. Now, if we do this 10 log, it will come out to be, this is in watt. So, it will be coming in dBW, it will come out to be minus 130.1 dBW. And if you look at the options, in dBW minus 130 dBm is there, it is not matching. So, let us try to see, there is a dBW minus 100, but we have a 130. So, look at it carefully. If I convert into dBm, it becomes minus 100.1 dBm. And now I see there is option minus 100.1 dBm. So, while looking at the options, you have to see what results you are getting, you have to convert them to the right unit and get the options, because intentionally here different types of options are given. So, just do not jump into none of this. So, we have matched the option with option B. So, the correct answer is option B. I made a silly mistake here, assuming that that was the distance, because I was looking at the distance as large number. This is the confusion always happens with large numbers. It is supposed to be kilowatt. So, since it is watt, it came out to be dBW. Then I converted it to dBm, added 30 to it, and we got the number. Now, let us look at the next one. This is a telemetry system. It is a very long question. Telemetry system of the satellite samples in sequence 40 sensors. So, 40 sensors data has to be sent, each producing 20 bits. So, each of the sensors 20 bits and 40 sensors. So, total number of bits will be 40 into 20 bits, and then add say 240 bits overhead to form a frame. So, the frame size in terms of bits are known now, 40 sensors, 20 bits and 240 bits, 40 into 20 plus 240 bits, and to form a frame, and transmits the data, that is that frame, at 1 kilobits per second to the control earth station. So, data rate is given and total volume of data is known, that is the frame size is known, and control earth station is 42,000 kilometer away. The question is, how long does it take to receive a complete telemetry data frame at the control earth station after the last beat of the frame has been transmitted, is transmitted by the telemetry. So, a frame is formed and there are options given. So, let us see which options, it is a time calculation. So, a frame is formed which has a header of 240 bits and the data is, each of them is 20 bits. So, there are 40 such things are there, total is 40 into 20, so many bits. So, total number of bits are 240 plus 800. So, that comes up to 1040 bits. This is a frame. Now, this is transmitted, the header goes first and this is the last bit, and let us say this is the satellite telemetry output out. So, it released from the satellite the last bit. So, this much will go out. How much time this 1040 bits will take? The time is frame time is 1040 by 1000, that is 1 kilobits per second, 1000 bits per second, that millisecond, which you can calculate and it will come out to be 0.14 second, sorry, it is more than a 1 second, 1.04 second, that is the frame time. And then it says that the satellite to earth station distance is 42,000 kilometer. So, there is a propagation delay is 42,000 kilometer, that is I converted into meter, and the velocity of light 3 into 10 to the power 8 meters per second. So, it, if you do this 42 by 3, then it comes out to be 0.14 second. So, last bit has gone out and from that time it took 1.14 second to reach the control station. At the control station, this whole frame has to go in. So, first is the propagation delay of 0.14 second and then the whole frame time which has to go inside till the last bit, which is 1.04 second. So, it is 1.18 second, the total time from the last bit transmitted from the satellite to the last bit received by the control station. So, the correct answer is 1.18 second, and the options 1.18 appears in option B. So, the option B is the correct answer. It is only the concept that it is the frame time and the last bit has to enter the control station. So, when it is released to when it is fully received, that is the total time, that is the delay, and it is critical because you have to know, you will come to know what happened at the satellite health parameter after 1.18 second. Okay. Let us take the next assignment, which is next problem, which is a satellite antenna makes a 3 dB angle of 5 degree to cover a specific region of the earth. Assuming 80% antenna efficiency, quite high, determine the gain of the antenna at 10 gigahertz. Now, sometimes you will find that the information given are more than what you need. You have to select the right information what you want to do these calculations. So, there are some extra informations are there. In earlier some also sometimes we had given some extra information which may not be required. So, do not try to use all the numbers which are given here, try to understand what is required. Now, this is very simple because we had given in terms of the 3 dB angle and the antenna efficiency the gain calculation, which is like this. The gain of the antenna, if I say capital G as the gain of the antenna, it depends on efficiency of the antenna, pi square 75 square and theta 3 dB square. This is 3 dB angle. The values are already given. This is 80% efficiency, and then pi square, and then 75 square, and this is 5, which is square 5 degree, which comes out to be 1776.53, and when you convert into dB, which comes out to be 32.5 dB, and it is compared to isotropic antenna. So, sometimes we call dB with respect to isotropic antenna dBi, and the options which are given are 48.7, 20.6, 32.5, 42.5. We got 32.5. So, 32.5 is a C. The correct option is C. Now, here the antenna efficiency was taken very high. Practically the antenna efficiencies are of the order of 0.6. So, this number, total number, can be estimated as a thumb rule, and these things I told in the class. 0.6 pi square 75 square is 33,300 some number. So, you can use that thumb rule also for many other calculations, but here the details are given. Now, let us take the question 6. Question 6 says again it is related to the power calculation with a solar cell, that is, find the number of solar cells required to generate end of life power of 5 kilowatt. Assume solar flux as 1100 watts per square meter, solar cell efficiency at end of life 10%, loss due to the shielding is 28%, and each cell, solar cell area is 8 square centimeter, and there are some options given for how many numbers of such solar cells are required to generate this 5000 watt. This is a straightforward calculation, and you have to put the on the expression, you put these numbers, you will get it straight. So, the expression, if you recollect, is the power that is end of life power is equal to the solar flux, the efficiency of the solar cell, each solar cell, 1 minus the loss due to shield, etc., number of solar cells, and surface area of the solar cell. And then obviously number we are asking. So, number of solar cell is P by phi, efficiency 1 minus L and S, where the value of phi is 1100 and value of E is given as a 10%, which is 0.1. This value of L is given as 0.28 and S is given as 8 square centimeter. We will be converting into meters of this, and P value is given as 5 kilowatt at the end of life. You put these values, you will get a number as 78914.14, etc. But then point after decimal 0.14 you cannot, we need more than this 78,914, more than this. So, therefore, your solar cell requirement will be 78915. You cannot use a fraction of a solar cell. So, 78915, and the options 78915, the option appears in D. So, your correct option is option D, right. Then let us see one more which is also related to reliability. This is serial parallel combination of reliability. Earlier we have seen only series reliability. A box consists of 4 identical components of equal reliability of 0.8 each are connected as shown in the figure below. Determine the reliability of the entire box. 2 are in series and then combination of that is in parallel, and the reliability numbers of the overall reliability inside of this system, which has 4 such subsystems connected like this, are given. Simple calculation, that is, you have 4 units, they are connected like this. We can think of a equivalent of that. This is the upper side, this is the lower side. So, these 2 series we can put as reliability of upper side, and these 2 we can put it as a reliability of lower side, and then we can say that this upper and lower reliability, equivalent reliability, is connected in parallel. This is the simple way. So, reliability of upper side each is 0.8. So, it is 0.8 into 0.8 series reliability. So, RU is 0.64. Similarly, RL also is 0.64, because they are also connected in series with the same numbers. And now, this RU and RL are connected in parallel. So, the total reliability will be 1 minus RU into 1 minus RL, which if you put the numbers, it will come out to be 0.87, and the option A itself is 0.87, none others are going near to it. So, answer is option A, simple calculation, series parallel combination. And now, question 8. This is for an interplanetary mission. Till now we were discussing on the satellite which is orbiting around the earth, etc. Now, we have just given a problem which is interplanetary. But let us see what is the problem. Interplanetary mission, the spacecraft receives telecommand consisting of header and command word. Telecommand, header and command word at 100 bits per second, very low bit rates. If the system is designed to accept header with up to 2 errors, you have to detect the header, and since it is a interplanetary mission, long distance, the possibility of a very weak signal will go. So, possibility of error is there. So, we will accept up to 2 errors. Then determine the minimum header length that is required for false alarm probability of once in 400 days. After 400 days, once in 400 days, one false alarm can occur. That is the system requirement. You can tolerate one error in 400 days at 100 bits per second with 2 error tolerance. So, what should be the header length? You have to design the header length, 2 error tolerance and such a false alarm rate. How do you do it? So, probability of false alarm once in 400 days is 1 by 400 into 86400, that is a day in terms of second. So, it is 2.89 into 10 to the power minus 10. And also probability of false alarm can be stated as, if you recollect from the class, I is equal to 0 to k, k is the number of errors we can tolerate, in this case k equal to 2, and the header size capital N and C I 2 to the power n. If you try to put and iterate to find out the n, and PFA value has been obtained, that is 2.89 into 10 to the power minus 10. So, from this if you go on iterating and you can find out which value in this combination of these sums will generate 2.89 or lower than that. PFA. So, this is equal to, it should be equal to or lower than that. Lower than that is obviously acceptable. Then you can find out by the iteration is n equal to 42, and the option B is n equal to 42. So, it is option B. You have to do this exercise I equal to 0, 1, 2. So, 3 sums will be there. Now, we go to the other problem, that is question number 9, and it says it is a very easy calculation, but the concept comes out. This is for end of life DC power of 6 kilowatt of a satellite. 80% of the DC power is used by the transponders, which has the power amplifier, and 20% is used by the others. So, majority of this DC power is taken by the amplifiers, the power amplifiers and related circuits. Each of the transponder has a DC to RF conversion efficiency of 25%. You can see how much we are losing really. So, 1/4 of that power is available to the transponders, and each of these transponder transmits RF power of 20 dBW. This much RF power each transponder transmits, and this is the total power what it gets. So, determine the number of transponders. It is a straightforward calculation, and options 10, 11, 12, 13 like that it is given. So, first let us see, it is given in some cases dBW, that is in dB, some cases it is given in watt. So, convert into one of them, better to go into ratio and go into the watt itself. So, each transponder I call TRP transponder transmits RF power is 20 dBW, which we convert into watt, it will become 100 watt. Now, the DC power, this is RF power. So, DC power drawn by each transponder, efficiency is 25%. So, 0.25. So, that is 400 watt. So, with 400 watt DC is generating RF power of 100 watt, 25% efficiency. And another information given is 80% of that 6 kilowatt taken by TRPs, all TRPs together. So, how much is that? 6 kilowatt multiplied by 0.8 is 4800 watt is taken by the all TRPs together. Each TRP is 400 watt. So, number of transponder, that is TRP, is 4800 by 400 is equal to 12. Straight easy calculation, and you have options 10, 11, 12, 13. So, C is the correct option. So, correct option is C. Let us take the 10th one. Now, it talks about the duration of the eclipse, how much battery, how many cells of the batteries are required. That is for the longest duration of eclipse. Here it is taken 72 minutes. If you remember, you calculated 69.4 minutes is the in the equinox in the GEO orbit. Here let us think that this is a orbit which is slightly elliptical orbit, or higher than GEO orbit. So, it is 72 minutes, just a number, do not worry much on that. So, 72 minutes we have to supply power from the battery. The power required to be supplied to the satellite is 4 kilowatt, that is the amount of power during the 72 minutes it has to be supplied. Now, each of the battery has a capacity of 93 watt hours. So, each of the battery cell. So, depth of discharge allowed is 80% with a discharge efficiency of 95%. If the mean discharge voltage is measured as 1.3 volt, determine the number of battery cells required, and numbers are given 50, 51, 52, 53, etc. This is also a straightforward, you put it into the formula. If you remember, the total power capacity of the battery is equal to the power multiplied by the duration it is required, a number of battery cells required, the discharge voltage, discharge depth, and the discharge efficiency, and T is equal to 72 minute. Since that is given in watt hour, so it is converted into hour as 1.2 hour. So, the values we want to find out n. So, n is equal to that is n will go up, c will come down. So, that is 4 kilowatt multiplied by the time 1.2 divided by 93 watt hour given c value, then 1.3 is Vd value, then 0.8 is d value, and eta d value is given as 0.95. You put them, you will get a 52.23. Since the fraction of a battery cell cannot be used, so it will be 53, and the options given are 50, 51, 52, 53. So, option D. D is the correct option. So, we have, I think we have completed all the assignment problems. You go through the video again, and you will see there are possibilities of many more questions that may come. Mostly you have to have a little understanding of the timing, as in the telemetry, and in the tracking and telecommand also there are certain in the tracking there is some range related issues that will be coming, and then the power and the battery relations are there, and there is payload and antenna related little information is available, formulas are there. So, you can solve more problems we expect. Thank you very much.